Hello, everybody, and welcome back, I guess. So we spent a lot of time discussing the Earth as a system, the various components of the Earth system, and so now we are going to really get into the sort of meat and potatoes of what is climate change in a sort of scientific, physical science sense. And so, in order to do that, we are going to need to talk in great detail about the radiation budget. And so that is the topic for today. We're going to talk about the radiation budget, and you'll see why this is so critically important for understanding climate change. Just a forewarning, there will be a lot of numbers and a lot of sort of physics concepts in this. Don't get bogged down by that. Make sure that you're taking notes. Make sure that you've got questions to ask me, and we'll go through it all. I promise that it will seem more complicated on the first pass, but as we get into it, it'll become more clear. First of all, what is radiation? We're talking about the radiation budget. We should probably define radiation, right? And some of you probably know what I mean by radiation. But for those of you who don't, or for those of you who need a little refresher, nothing wrong with that. Radiation is just electromagnetic energy. It's energy that is put out there into the universe of varying frequencies and energies and wavelengths, and we typically categorize the type of radiation according to where it falls on this electromagnetic spectrum. So radiation, electromagnetic radiation, when we talk about radiation, is a form of energy that can be characterized by its wavelengths, both the frequency at which the wavelengths sort of repeat themselves, and also the amplitude of the wavelength itself. And so not typically, all the time, electromagnetic radiation that has short wavelengths, right? So the waves are very close together, super short, has a very high frequency, we say. So it has a very high frequency wavelength because the wave peaks themselves, right? Each individual peak, they're very close together. And therefore, this type of energy has radiation. Has high energy, okay, and then that will typically fall on this end of the electromagnetic spectrum. Then there's electromagnetic radiation that has longer wavelengths, right, which means it has a lower frequency and therefore a lower energy, and those forms of radiation fall on this end of the electromagnetic spectrum. So high energy, high frequency, short wavelength radiation is typically called gamma ray, for example, or X-ray, or even ultraviolet radiation. These are all small wavelengths, short wavelengths, high energy radiation. And then on the other end of the spectrum, you have low frequency, long wavelengths, low energy radiation, like radio waves or microwaves or infrared even. And then right kind of sort of smack dab in the middle of that, we have the visible light portion of the electromagnetic spectrum. This is the only form of radiation that our eyes can see unaided. Okay, so when you look around you, the reason that you see things is because visible light is either being emitted from them or bouncing off of them, being reflected off of them into your eye, and therefore you can see them. So why can we see visible light? Why did we evolve as humans to see visible light but no other type of radiation? We'll get to that in a second. But before we do, we have to discuss this sort of complicated physics concept, which this graph looks very complicated, I understand, but this concept is actually not as complicated as you think. So Planck's law. Planck's law relates how much power density is emitted from an object, right, versus the wavelength of that radiation that's emitted. So Any object in the universe, any object, whether it be this glass, my face, the lamp behind me, anything, if it has a temperature, then it's emitting radiation. And if it has a temperature and is emitting radiation, we call that object a black body. Pretty much everything in the universe is a black body. It has a temperature and is therefore emitting radiation. But how much radiation and what wavelength of radiation that object emits depends on its temperature. Okay, so so Planck's law, the graph that sort of explains Planck's law, shows on the x-axis the wavelength of radiation that's being emitted from that black body versus how much radiation at each of these wavelengths is being emitted. So you can see that for all black body objects, they follow a similar curve. Very little radiation is emitted at the shorter wavelengths. There is a peak somewhere at some wavelength, depending on the temperature of the object, and then it slowly tapers off to longer wavelengths. The cooler the object is, right, the lower the temperature of the object, the lower this peak will be, and the further towards longer wavelengths it will be. So a cool object, for example, a 3000 Kelvin object, is going to emit much less radiation than a 6000 degree Kelvin object. It's also going to have a peak in radiation emissions at longer wavelengths than the warmer object. So hotter objects emit radiation at generally shorter wavelengths and more irradiance, more energy is actually emitted. Cooler objects emit radiation at longer wavelengths, but less irradiance, lower energy that's actually emitted. And one of the most important black bodies in our world is the sun, obviously. So the sun is up there, millions and millions of miles away. It's hot as hell, and so it's emitting a lot of radiation as a black body. It's very hot. Okay. Not all of the radiation that it emits comes to Earth. In fact, a very small percentage of radiation emitted by the sun actually finds its way to our planet, right? Most of it is sort of spread out spherically around our solar system. And most importantly, the sun, which has a temperature of about 5,525 degrees Kelvin, is a very hot black body, so it emits a lot of radiation at relatively short wavelengths. And so we can see this black line is the idealized curve for a 5,525 degree Kelvin black body. So for a black body of this temperature, physics predicts that very little radiation will be emitted below 250 nanometer wavelengths. A lot of radiation will be emitted between about 300 and 700 nanometer wavelengths. Okay, and then the amount of radiation that's emitted from that black body slowly decreases as the wavelength increases. So you can see that the sun, which is about this temperature, the curve for the sun, the measured curve of radiation for the sun, lines up pretty well. That's this more jaggedy curve here. That's the actual radiation that we measure coming off of the sun. That's because the sun is not a perfect 5,525 degree black body all the time. It's changing its temperature just slightly, and that can change sort of where the radiation, what wavelength radiation is being emitted. But in general, you'll see that the peak in radiation being emitted by the sun falls in the visible part of the electromagnetic spectrum, which means that the vast majority of radiation that's being emitted by the sun is being emitted in the form of visible light. Now, some radiation, all this radiation, is being emitted in the form of ultraviolet light. That's the slightly shorter wavelengths, right? The shorter wavelengths, but higher, more energetic radiation. And then a fairly large and substantial portion of radiation being emitted by the sun is being emitted in the infrared part of the electromagnetic spectrum. But Still, far and away, the vast, vast, vast majority of radiation being emitted from the sun is being emitted in the visible part of the electromagnetic spectrum. That's why we have evolved to see visible light, to interpret reflected or emitted visible light. That's why our eyes can see it, because most of the radiation, the vast majority of radiation entering our Earth's system, is coming from the sun in the form of visible light. And so therefore we have evolved to see visible light. That's really the only reason, okay? And the reason the sun emits most of its radiation as visible light is because of its temperature. If it was a little bit hotter, then most of the radiation that it emitted would be in the form of ultraviolet light, perhaps. And if it was a little cooler, then perhaps most of the radiation that it emitted would be in the form of infrared radiation. But because its temperature is what it is, the sun is as hot as it is, most of the radiation that's being emitted from the sun is in the form of visible light. And we call this radiation solar radiation. I've got my trusty whiteboard here, and so I'm just going to write that term on here so that you have it for reference. So solar radiation is short wavelengths, mostly visible light, and comes from the sun. So that's solar radiation. Great. And so that's solar radiation coming towards the Earth from the sun, enters the top of our atmosphere. A certain amount of it enters the top of our Earth's atmosphere. And so that portion of the radiation budget is called the incoming portion, right? So this is light that is incoming into the Earth system from outside of it, in our case from the sun. And that incoming solar radiation is solar, or as this graph shows it, short wave radiation. Okay? Now, all of the radiation that comes in from the sun doesn't stay here. In fact, 30% of it is reflected. It's reflected by three very bright types of objects in our system. I mean, it's reflected by everything that can reflect it, but in general, these three things reflect the vast majority of the solar radiation coming in from the sun. Do you have any guesses what those three things are? I'll give you a second, think about them, and then you can confirm if your guess was right. So three things that are really, really reflected, that reflect most of the radiation coming from the sun. Okay, those things are clouds, very white, snow and ice, also very white, and deserts, not white, but very light colored. So 30% of the radiation that comes into our atmosphere is reflected. That's known as Earth's albedo. Albedo is a term that refers to the amount of radiation coming from the sun that's reflected. This means that 70% of the radiation coming from the sun is absorbed. So here's sort of a depiction of that, right? So you have incoming solar radiation. Most of it is absorbed by the Earth. Some of it is reflected. Some of it passes directly out into space. And then we're going to talk about this second sort of major component that's over here. So this shows a difference between the sunlight at the top of the atmosphere, right? The solar radiation entering the top of the atmosphere, where most of it's coming in the form of visible light, and versus the sunlight that makes it down to the surface of the Earth and is therefore absorbed into the Earth's system. That's the red curve here. So you can see that quite a bit of visible light is reflected, but also quite a bit of infrared light at these random wavelength bands doesn't make it to the surface of the Earth. And quite a bit, a vast majority of the ultraviolet light coming in from the sun does not make it to the surface of the Earth. So most of it is absorbed by gases or reflected by clouds and other things. So the comparison between what comes in at the top of the atmosphere versus what makes it to the surface of the Earth, this is about 30%, right? The albedo is 30%. 30% of the radiation from the sun is reflected. That's an important number for you all to remember. Of course, it's not distributed evenly across the globe. Most of that sunlight is entering the Earth system at the equator, which means that there's got to be some movement of that energy around the planet in order for the whole planet to sort of have a similar temperature. Thinking physics-wise, right? The difference between the pole and the equator is extreme to our human body, but in physics, it's not a super extreme difference. So most of the sunlight, most of the solar radiation is received sort of here at the equator, right, with the dark reds. Much less of it is received here at the pole, significantly less, 10, 20 times less. And this is just because the Earth is round. But this means that that energy is going to have to get around the globe, okay, through weather, mainly. And that's how we distribute the radiation across the globe. Okay, so sun is a black body. The sun is an important black body. There's solar radiation, incoming solar radiation, all very important. That's the incoming side of the radiation budget. Now, just because it's a budget, there needs to be an other side of the equation to balance it. We want this equation to be balanced. We want the incoming solar radiation to equal the outgoing solar radiation. So how is there outgoing not outgoing solar radiation, outgoing radiation. So how is there outgoing radiation? Well, there's outgoing radiation because the Earth also is a black body. The Earth has a temperature, right? And as we defined in the beginning, all things with a temperature emit radiation. Therefore, the Earth, which is much cooler than the sun, is still a black body. It just, because it's cooler than the sun, it emits radiation at a different wavelength. It's cooler, which means that it emits radiation at a longer wavelength. Okay, that's why the curve is shifted towards the longer wavelengths, and it emits less overall radiation than the sun. Now, we're much closer to the Earth. We're on the Earth. So we feel basically all of its radiation, right? We're present for that. Whereas the sun, we're very far away from, and we're just a little tiny dot compared to the sun. So we receive only a very small fraction of the sun's radiation at the Earth. And so therefore they balance each other more than you might think. But the Earth is much cooler than the sun, so it's emitting less radiation at longer wavelengths. And just to put that sort of in proximity to other things that you might, recognize, right? The sun, which is much hotter than the Earth, is emitting radiation in the visible spectrum mostly. The Earth, which is much cooler than the sun, is emitting radiation mostly in the infrared part of the spectrum. So most of the Earth's outgoing radiation is in the form of infrared light, okay? Infrared light. And we call this type of radiation, I'm going to bring back my whiteboard. We call this type of radiation terrestrial radiation, or creatively, long wave radiation. So the sun's radiation is solar radiation or short wave radiation. The Earth's radiation is long wave or terrestrial radiation. So then it has longer wavelengths, mostly infrared radiation, and it comes from the Earth. Okay. Great. So most of what Earth emits, most of the long wave radiation that Earth emits, never quite makes it directly to space. Okay? So the Earth emits a lot of radiation, a lot of terrestrial or long-wave radiation in the form of infrared radiation. Because it's infrared radiation, it behaves differently in the atmosphere, okay? And so it comes up from the Earth's surface, and it gets into the atmosphere where it is absorbed, okay, by some gas molecules that are in the atmosphere. And much of it then actually comes back down to Earth. Some of it escapes off into space. And this process is known as the greenhouse effect. Okay, I'm going to skip this figure. And so that is how we complete the radiation budget. We have incoming solar radiation, right? Incoming from the sun. 30% of it is reflected by clouds, by deserts on the surface, by ice on the surface. Okay, so that means that 70% of it is absorbed by both the surface and the atmosphere. Then the other side of the equation, we've got the long wave or terrestrial radiation being emitted from the surface of the Earth up into the atmosphere. Most of that gets absorbed by the atmosphere through a process known as the greenhouse effect. Now, I am going to draw what happens with the greenhouse effect. Like, what is the deal with the greenhouse effect? So here we go. So with the greenhouse effect, right, let's see. Let's draw our surface. We've got some trees and maybe a city. Okay, some trees. Okay, here's our surface of the Earth. I'm a very good artist. All right, so the surface of the Earth, right? The Earth is a black body. So we know that the Earth is emitting long wave radiation, terrestrial radiation, infrared radiation, which I'm going to abbreviate here as infrared radiation. Now, in the atmosphere, there are several important gases, which we call greenhouse gases. And those greenhouse gases are, there's 4 major greenhouse gases. There's carbon dioxide, methane, nitrous oxide, and water vapor. So those gases are floating around in the atmosphere, and those gases in the atmosphere are really, really, really good at absorbing, coincidentally, infrared radiation. So let's draw those gas molecules. I'm just going to draw carbon dioxide because that's the most famous one. So those gas molecules, they absorb the infrared radiation coming off the surface of the Earth because they're good at it, because they're good at absorbing long wave infrared radiation. So we've got these carbon dioxide molecules absorbing infrared radiation. Now, what happens when those molecules absorb that infrared radiation? They absorb this radiation, That means that they now have a temperature, right? Because they're absorbing this infrared radiation. They're warming up. They have a temperature. They each become individually a black body. Just like the Earth, just like the sun, just like everything. Each molecule of greenhouse gas, carbon dioxide, whatever, absorbs this radiation, becomes a black body. That means it too is emitting its own radiation. And it's emitting infrared radiation. About the same temperature as the Earth. So I'm just going to draw this. So they absorb infrared radiation. So here is my depiction of the greenhouse effect. I'll write that up there and then show you one more time. You can maybe pause it. So because those are all emitting radiation, that radiation is bouncing all around the atmosphere, and the vast majority of it directionally ends up coming back down towards the surface of the Earth. Okay? Most of that radiation that's being emitted by those greenhouse gases ends up coming back down towards the Earth. Some of it does escape to space, okay? But the part that does not, the part that comes down back to Earth, is what keeps us warm. It's what keeps us a habitable planet. So most of it comes back down to the surface of the Earth. This is my depiction of the greenhouse effect. All right, good. So now we all understand the greenhouse effect, right? So what makes this a balanced budget? So we've got the radiation that's incoming from the sun, right? That's up here. 30% of it is being reflected. 70% of it is being absorbed. Now the Earth itself is emitting this long wave terrestrial radiation. Much of it is getting absorbed in the atmosphere by these greenhouse gases, re-emitted back down to the Earth's surface. Some of it is escaping out to space. The only thing is what's escaping out to space after the end of all that must equal the amount that is coming in from space. So in this figure, 340 watts per meter squared of radiation is coming in from the sun, 100 is being reflected, 239 is being emitted through thermal or terrestrial outgoing infrared long wave radiation. So if I add up what's going out, I get 339. If I add up what's coming in, I get 340, which means that there's slightly more coming in than going out. So the radiation budget is out of balance. And it's out of balance because there's more and more greenhouse gases every year, which increase the greenhouse effect, which increase the amount of radiation that stays trapped by the atmosphere and decreases the amount of radiation that ultimately makes it up back out to space. So the sun is not changing. The sun is not changing at all. The amount of greenhouse gases in the atmosphere are increasing the greenhouse effect, which is lowering this number. As this number goes down, this radiation balance continues to get more and more and more out of balance. Okay? Think of the greenhouse effect as a blanket. In the winter, it's cold, and you put a blanket on your body. That blanket on your body, what it's doing is it's actually trapping the heat that's coming off of your body, which is also a black body, just like the Earth, just like everything, right? It's emitting radiation. That radiation goes up into the blanket, where the blanket itself, absorbs that heat, re-emits it as infrared radiation back down to your body. That warms your body up. The greenhouse effect increasing is like putting an extra blanket on the Earth. You put an extra blanket on the Earth, it's going to be warmer under that blanket, right? Warmer and warmer under that blanket. Slightly cooler outside of that blanket, right? Slightly less radiation making it through the blanket. That budget, which was once in balance, is now out of balance. You're going to get warmer and warmer and warmer under that blanket. That's great news if you're cold in the winter. It's not great news for our planet, which is experiencing climate change or global warming because of this process. So I'm going to sort of wrap up this conversation with this figure, which is kind of a disaster, but I'm going to walk through it. So we look at all of these different things in the atmosphere, or things that we've done or haven't done to the Earth system, and we calculate how much their changing concentrations influence the radiation budget. For example, as we put more and more carbon dioxide into the atmosphere, the greenhouse effect gets stronger and stronger, and it pushes the radiation budget out of balance by a certain amount. Using sophisticated models, using our physics information, physics knowledge, and information about historical atmospheric concentrations, we can estimate that just the carbon dioxide that humans have put into the atmosphere has thrown the radiation budget out of balance by about 1.68 watts per meter squared. That's what this number is referring to right here. Methane, it's about 1 watt per meter squared. Other nitrous oxide, for example, 0.17, carbon dioxide, NOx, etc. They all have different, what we call, radiative forcings. And if we add them all up, we estimate that as of 2011-2012, humans have put things in the atmosphere, have disrupted the atmosphere so much that the radiation budget is out of balance by 2.3 watts per meter squared. That means for the amount of incoming solar radiation, right? For every moment, or not for every moment, for the sum of all moments from before we started doing, fossil fuel burning to now, we have thrown the radiation balance, meaning the amount of radiation that has left the atmosphere is 2.3 watts per meter squared less than the amount that's coming in, which means that the radiation budget is out of balance by 2.3 watts per meter squared. There's 2.3 watts per meter squared extra radiation now in the Earth system. Seems like a small number, but actually when you multiply it by the area of the Earth, it's actually a huge amount of radiation. So this means relative to 1750, when the radiation budget was in balance, our Earth system has absorbed 2.3 watts per meter squared more of extra radiation, excess radiation. And this is climate change in a nutshell. This is how you end up with a warming planet. You have a radiation budget that's out of balance. It's all about the energy budget. It's all about energy coming in minus energy going out. I'm going to leave this up here. You can take a screenshot of this if you so desire. This is just another depiction of the greenhouse effect. I think personally, my drawing is better, but that's just me. I'll also leave this here up for reference. I'm not going to explain it right now. I will explain it in the Zoom if you've got questions about this, the atmospheric window, absorption of different gases, etc. Same here. So I want to close this off by saying the temperature response, right? The actual global warming is a response to the radiation imbalance. You need that energy imbalance to drive a change in the Earth's temperature. So the carbon dioxide itself is not directly sort of driving the temperature up. It's changing the radiation budget. It's changing the balance of energy in the Earth system. And that, the fact that it's out of balance is what is causing the temperature rise. And so we see it in a number of records dating back 1,000, etc. years. We can see in all of these records in the last 150 or 200 years, the temperature of the planet has increased significantly. And this increase, which is highly anomalous compared to the last 1,000 years of temperatures on the Earth, is being driven by an out of balance radiation energy budget on the planet. It's as simple as that. It's as simple as that. In fact, one of the first papers to write about this imbalance, to write about this so-called greenhouse effect, was a paper that was published 125 years ago by Svante Arrhenius in 1896, and we will discuss that paper in detail in this class in a coming lecture. So we have known about this, we have knowledge about this, we've understood this for a long time. It really is as simple as the radiation budget is out of balance because the greenhouse effect is getting stronger and stronger. This is driving a temperature response, which is driving all of the other changes that we have seen in Earth's climate. Okay, so hopefully you've got lots of questions on this. It's a super important topic, and we'll get into the nitty-gritty when we meet together on Monday on the Zoom. All right. I hope this was not super confusing.